I'm going to talk about a model of glass dynamics. In this talk, we'll tackle the following question from a mathematical perspective. Does a glass melt faster than it relaxes? Imagine you take a piece of glass and you put it in your freezer at low temperature and you measure how long it takes for the molecules to forget their initial positions. Then you take it out and you throw it in boiling water and you measure how long it takes for it to melt. What we would like to know is if, as intuition suggests, the melting is much faster after a quench from low to high temperature than the relaxation at low temperature. Structural glasses have been a subject of debate in physics for at least half a century now, and there are many competing theories that have not reached consensus yet. One such theory suggests that the liquid glass phase transition has little to do with ordinary equilibrium phase transitions, but is rather caused by kinetic constraints which slow the dynamics of the material down. One of the most classical such kinetically constrained models is the one I'm going to define next. It's called the Fredrickson-Andersen model, after the two people who introduced it in the 80s. It's a continuous time Markov chain on the state space black-white to the power of the square grid. So on each side of the square grid you have a state. You're given a parameter Q, which is the equilibrium density of black sites. And why do I call it equilibrium density? Because the product Bernoulli measure with parameter Q will be reversible for this dynamics. Let me first go with the Glauber dynamics that you may have heard of. In the Glauber dynamics, what you do is you resample each site independently at rate 1 from the equilibrium measure. In other words, on each site at exponentially distributed intervals of time with mean 1, you toss a coin which is Q biased and you change the state to whatever the coin tells you. Now, in the FA dynamics, what you do is you perform your Glauber dynamics, but with an important twist. If at the time when you update a current particular vertex, it has less than 2 black neighbors, you don't perform the update. So here's what that gives on an example. If this is your current state, and you try to update this red vertex, then it has 2 black neighbors, so you are allowed to update it. And maybe the coin that you toss tells you white. So you change it to white, but it was already white, so we don't do anything really. Then maybe you try to update this vertex, which has 3 neighbors, which is also enough. So you're also allowed to update it, and maybe the coin tells you white again. So you change it to white. Then maybe you try this vertex, and it has only 1 black neighbor, so you can't do anything regardless of what the coin tells you. So you don't do anything, and you go on like that. The initial state we will take will be a product Bernoulli again, but with possibly a different parameter, which will go to 0, and that will correspond to low temperature in our glass. The quantity we will want to investigate the behavior of is the persistence time, which quantifies precisely what we're interested in, namely how long it takes to forget the initial state. And the persistence time is defined as the first time when the origin changes state. Now, one more model that I need to define, which is really a particular case of the previous one, is Bootstrap percolation, introduced in the 70s, which corresponds to Q equals 1 in the previous model. So in other words, what you can say is that you no longer need your coin, but whenever a site has 2 black neighbors, it also becomes black at exponentially distributed time with mean 1. So here's what we know about the persistence time in this Bootstrap percolation regime. I don't expect you to take in this much information, but also I won't tell you about the full history of the problem. But what you can take in from this theorem is that we know the leading order term in the asymptotic expansion, if you want, as p goes to 0 of the persistence time. It's this expression. And we also know the second term, the corrective term, up to a constant factor. Now, the second term is exactly what we got with Rob Morris with quite a lot of work and a few new ideas. We managed to remove this polylogarithmic factor here and get just a constant in the lower bound. Now, all results in Bootstrap percolation, at least the ones cited, come from the following principle. There are certain patches of black sites which, if they are large enough and they are well structured enough, then they are able to easily grow, and they grow fast, and they invade the entire plane. So all the game is to have a good control of what those droplets are and how rare they are. And that's what gives such results. Now let's go back to the freezer case. Namely, we look at equilibrium, so we take the initial density P to be equal to the equilibrium one Q, and they both go to 0. So remember that now we are able to remove black sites, and that's actually what we will usually do, because our coin is biased very much towards white. Now, a priori, it's not clear whether the persistence time in this regime, which is very different from the Bootstrap percolation regime, should be closely related. And physicists over the years conjectured several times that it should be very different. Now, it turns out that's not at all the case, and the expression is extremely similar, for the only difference with Bootstrap percolation being the factor 2 in the leading order term. The second order term is the same here in the lower bound, and we know it a bit less precisely in the upper bound for now. Now, things for the equilibrium case were developed a lot later, and even with the last year's improvements on the upper bound, we still didn't know the exact first order term even up to a constant factor. However, what we managed to get with Fabio Martinelli and Cristina Toninelli in an upcoming paper is not only the first order term, but we also narrow down the second order term a lot. Now, for FA at equilibrium, the lower bounds are quite easy in the sense that they follow easily from Bootstrap percolation results, which may be hard, but we take them for granted. And in this particular case, what we use is exactly the Bootstrap percolation result I told you about by Morris and myself to get this lower bound. The upper bounds are a lot harder, and what you need to do there is to have a good mechanism for moving efficiently a droplet to the origin, and you want to do so without creating many black sites, because they're unlikely. Now that's a bit tricky, because black sites are exactly what allows you to move, so it's not that easy. In any case, what we get from these two results is that the equilibrium persistence time in this model is, to a very high precision, the square of the one in the Bootstrap percolation regime. So in some sense, the melting of this glass is not that much faster than the relaxation at low temperature. Now, I should mention that this square relation is first not at all automatic, and actually it doesn't quite hold in general, but it's also as close as the two quantities could get in 2 dimensions. One nice thing about the proof that I told you essentially nothing about is that it's quite robust, and it applies to various related contexts, including higher dimensions and higher thresholds. So to conclude, here are the 2 papers that this talk is based on. The first one you can already go check out if you're interested, and the second one will hopefully be on archive sometime soon. And one last thing, a piece of advertisement, if you would like to learn about a broad framework of kinetically constrained models, among which the FA model is central representative, you can go take a look at Laure Maréchais' talk at this very symposium and at this very session. Thank you for your attention.